So I think it is about time. So my name's Chris. I'm with Tendril. We're over here in Boulder. We work in the smart energy space. We use Scala and some other stuff. And today I'm going to talk about laws, but I'm going to start by talking about monads, as you do. And don't get upset here if you don't understand everything. I'm using this as an illustrative example. So monads, right, they're this kind of summit that a lot of people see off in the distance as they start their functional programming journey, and it's a mountain that they're trying to climb, and they learn many things along the way, but it's kind of one of those big signposts out there. You hear about it in talks, you read about it all over the place. You're trying to figure out what it is. You see all these tutorials. Everybody's got a monad tutorial. You know, monads are burritos and elephants and lenses and pipes and who knows what else. Eventually some smartass comes along and says, oh, they're just monoids in the category of endofunctors, as if that helps at all. But it takes somebody kind of to be pragmatic and say, monads are classes that have these two kind of methods, right? And, these have kind of different names. Apply could be return or unit, or pure. Flat map, could be bind or join. But it's really kind of, these things have these shapes. But wait, it's a little more than that, right? It's about these have well-behaved methods, right? These things don't just exist with a name, they have to work a particular way. And so, right, what's the first part of how they behave is the signature. So we have a type signature, they have to conform to that. Okay, that gets me part of the way. But then there's also behaviors. And so there's these kind of properties that we have to make sure that these methods handle. There's maybe some kind of left identity that says if you apply and then flat map, it's the same as just calling the function. Maybe a right identity thing. If you flat map apply, it's the same as just taking your starting instance. Some associativity stuff about the ordering of the chain or the nesting of the chain. And these kind of properties, we call these properties laws. So I'm going to be talking about laws and how to test laws. My kind of overview, we'll talk about the benefits of them. I'll kind of review the typeclass pattern as it is implemented in Scala. We'll talk about property testing, which is a way that we'll get into being able to test these laws against an instance of a type class. And we'll look at how Scala Z and CATS both do these so that you can test your instances written against either of these libraries. So, benefits of laws. So laws specify behavior. They kind of say how the various methods within that type class are going to interact with one another, right? We saw the monad laws a couple slides ago, and it was about how pure and flat map in one order or another, how they're going to interact against each other. And that leads you to kind of the equivalence of different ways of manipulating your instances by calling their methods. And what this gives you is the ability to be consistent with algorithms that are going to use your instance. You're going to know that you'll be able to take your instance and send them to somebody else's library that operates on monads. And as long as you have written your monad following the laws, you can be confident that it will work appropriately with their algorithm. And for both you as an implementer of an instance and with a different hat on you as an implementer of an algorithm, they give you some constraints on what you can implement, and they give you some assumptions that you can make about what's safe and what's not safe when you implement them. So for instance implementers, these constrain our possible implementations. You can't do something completely stupid and off the wall, or your laws are not going to work. They're going to disallow incoherent approaches. So if our maps and our flat maps don't conform to one another and work in different weird ways, the law will help show us that we have not written a good instance in that way. And again, that gives us confidence that when we pass this off to some algorithm that's going to operate on our type class, it's going to be able to work with ours correctly in context. And then as an algorithm implementer, these are going to give us some assumptions that we can make about what's safe to write in our code. Give us expectations that we can expect about those type classes that are being passed to us to operate upon, and gives us some confidence that the instance that's given to us will behave, again, in our context. So kind of what do I mean by assumptions of what are good expectations that you can have? So a few examples here. So monoids are about combining things, right? Laws, we have a left and a right identity, and these tell us something about zeros not changing the value, depending which side we put zeros in on. So what does this assumption mean? This assumption means that I can stick zeros in places, and it's going to work. So I could split up a bunch of things, add zeros in order to balance them out, things like that. Functors are about kind of mapping from one context to another context. Identity is a law on that, and it says that if you map the constructor form, it's not going to change the value. So let me go to the next one. Composition on a functor tells us that it's safe to rewrite chains into composition. So again, I can break up work into different places and combine them together using composition and know that that's going to be safe. When we get to monad, we have left identity is about flat map using the result that came back from the function, so we can know that we don't have to keep history. We can just do chain our operations and use things that came from the last one, so on. So these are the kind of things I mean by assumptions that we can make as implementers based on knowing that these laws are going to hold, or expecting that these laws are going to hold. So let me do a review of the type class pattern. Who here is familiar with doing type classes in Scala? Okay, a little more than half the room, so we can go through these pretty easily. So type classes in Scala are about external implementations of some interface. So without access to the code, to a piece of code, we can write a type class around that code, right? So, so I don't need to open up a class and add and extends and write some functions directly into it. I can write a monad instance around something that I get from some library in order to now use it in another place. These get introduced into algorithms as implicit parameters. You might do that directly as an implicit. You might do it with a context bound. Either way is equivalent. Context bound is going to introduce the evidence, the implicit evidence from the compiler. And what's really nice about type classes is that we can implement in terms of other instances. So if I have, say, an adder for ints, I can now write an adder for pairs of ints by relying on the adder for ints. And then we can actually take that up a little bit further. I don't need to know what that t type is. The compiler gives it to me. So as long as the compiler can give me an adder for t, I can make an adder for pairs of t, and I don't have to know about all possible types that I would ever need to build an adder for, an adder of pairs for. So how do you build one? You define an interface, implement it appropriately for your class. The class that you're trying to do may come from you or may come from another place. You introduce that into implicit scope because the compiler is going to wire this all together as implicits. You pass it into your function as an implicit parameter as a type constraint, and then you can call methods on it within your algorithm. So I have an adder trait. I've parameterized it in A. I can make an adder instance for integers by implementing this add method, and in this case, he's just delegating to the regular plus. I'm going to add that to implicit scope, which I've done there when I made it a new instance. Now my algorithm is this add things. He's going to take a t which has an adder instance, so the compiler is going to introduce an implicit evidence, which is that instance that it found in an implicit scope. And then I can summon it to call methods on it by using the implicitly keyword. And then I can call its add method. So then I could say add things 5, 7. And I could use this same add things method if I had other instances, if I had double adders, pair adders, float adders, etc. And we can build these up inductively, right? So in this case, I'm not doing adder, I'm doing pairs. Pair is parameterized in T. It just has two things, a first and a second. I've made up my pair adder now be an adder for pairs. And it's going to take a T, which has an adder instance. And I'm going to delegate, so I use implicitly to summon it into my scope. And then I'm going to delegate to its add in order to add my first and second. I'm just going to line up, add the first, add the second, and there's my pair. So that's how I make an adder for pair out of an adder for some type T. So I thought I had another slide in here, so how can we now prove that this pair adder works? Well, so maybe this isn't quite the right example. If we had laws for adder, say, how would I prove that this adder satisfied those laws? Well, one way I could do is the substitution method, right? Substitution method uses equational reasoning and referential transparency, and it says that we can replace a call to a method with the body of that method, right? And then we can, by hand, rewrite that, do code algebra, essentially, right? And replace these things and work our way through, and we can prove it on paper. And there's plenty of examples of this. You can find them online. I think Odersky went through it in one of the Coursera classes and so on. But that's not really interesting. We want to be able to write our code and test our code. So a thing that we're going to have to start using, or a technique we can use that starts getting us to that, is property testing. So property testing is about going from very simple, this input should be this output sort of tests, to a higher level of logic and saying, here's a property that should hold for a whole bunch of inputs and their corresponding outputs. And what we're going to do is we're going to call, we're going to repeat our test a whole bunch of times on random data and see that those properties always hold. And oh, by the way, it's probably not purely random. The frameworks that help us with these are going to give us some kind of biased random to try to provoke interesting edge cases, right? So they're going to give us more likely to start with zeros and maxents and minus maxents and things like that. But it's generating a bunch of instances, calling our test, and then seeing if that property held. And then likewise, these frameworks have this nice feature at the other side, which is test case minimization, where once the thing is falsified, they'll try to make the input smaller and still be falsified. So if it fails with a very huge list, it'll try to break it down and give you the smallest list that it failed with. I'll take questions at the end if you don't mind. So generating random data for these, we're going to build it up with a couple of things that the property test framework provides for us. We have a gen. Gen lets us generate values of different types in a bunch of different interesting ways. We might be able to pick one from a list of things. We might be able to choose from a range. We might be able to add these predicates such that it's an even number. And we can build them in terms of each other, right? So we can take two chosen ints and use those to build the pair. For any arbitrary type that we have, we can build a typeclass instance for arbitraries that let us generate these. So here I've got an arbitrary Boolean example. I'm going to use one of, which is a gen form, one of true or false. So I've made now a typeclass instance for arbitrary Boolean. If I have, this other one is for a my option type, which I show later. Given some other arbitrary instance for t, I will say that I will generate a my option, which is either a my sum or a my none, where the my sum contains a value that's generated from the from that t's arbitrary instance. So with that, we'll be able to call and generate a bunch of random stuff, apply that to our law test, see if the properties hold, and go from there. So that's pretty cool. How does that work in Scala Z and in cats? So so one of the property testing frameworks that I kind of alluded to there, Scala check. Scala check's one of the most common ones. Scala Z uses Scala check directly. Scala Z implements a list of laws together with the abstractions. So where monoid is defined in Scala Z standard, the monoid law subtrait is defined there as well. And so an example of that, the monoid law extends the semigroup law. It has a def for left identity. It has a def for right identity. And because it's extended semigroup, it's going to pick up semigroups laws as well. There's then a separate side library, Scala Z, Scala check binding, which will provide us the mechanism to tie that together and actually call those tests. So I have my pair of t. I make a monoid instance for pair of int. There's kind of some reasons here. This could be generalized a little bit more, but for example purpose, we've made this concrete pair of int. So monoid has two methods that we have to implement, a 0 and an append. So we will delegate to the int monoid for both of those things. So we'll make our pair by doing 2 zeros. And then we'll do our append by appending the firsts together and appending the ends together and building the pair. In order to then do my property testing, I'm going to need an arbitrary instance to generate instances of pair. So that's going to use gen choose to choose a first int, second one to choose a second int, which is based on the first, and then yield the pair of those two things. So that'll give me pairs. And then I need some way to show that they're equal, or to test that two instances are equal. And I do that by implementing the equal type class, which has a single method equal, takes the two pairs, returns a Boolean. And this one is straightforward. Both the firsts are the same, both the seconds are the same, they're the same. Once I have those, now I can start wiring this into a test. So I'm using Scala test here. I've got flat spec with matchers. I have whatever else, other tests that I want to have. I pick up check all from Scala Z Speculate. In order for me to get this to work, I had to go around and play with some other code. I'm still working on getting a really good example of pulling that in directly. Stuff is kind of buried. So I worked around that. And now I can call check all the monoid laws for pair of int. So I could have called this, check all monoid laws for whatever type, check all monad laws for an instance, and so on. And we run that, and if everything's happy, we'll see, okay, passed 100 tests, okay, passed 100 tests, okay, passed 100 tests. Should have a working 0, should have a working append, should test laws. So all these okays are coming from the property test for each of those laws. So we had our two monoid laws, and then we must have picked up a third from our semigroup, and those three okays all are is running 100 tests each of those laws, checking to see whether the property still holds. And if so, everything's happy. My should test laws is green. My should have a working zero and should have a working append were tests that I just had myself. So again, we talked about separating out the behavior as specified in the laws from whatever domain behavior my own type has. So I want to make sure that that my zero works the way I think my zero should work, and my append does whatever my append should do, whereas the testing laws test that the laws hold and that the behavior of these is right and consistent. If I do one of those wrong, and my laws no longer hold, then I will see an error when the tests run at the beginning, when the property tests check. It'll tell me it falsified after however many past checks. This is the input that it failed on, this pair 11420. Not sure why that doesn't tell me what it expected, but that's what it saw. And then we'll see, we see that the other one is my working append not working, because in order for me to break the law, I also broke my other test. So this method that I found in order to call these and make it work obviously didn't tie into Scala test quite right, so it still showed me that the laws passed. So I'm not sure what's up with that. Hopefully I can iron that out before I post the example. Cats. So whereas Scala Z used Scala check directly, Cats uses this side library called Discipline. It's a type level project. It builds on top of Scala check and does a lot of that same kind of interacting with the lower level library, providing the mechanism to make that all work. Discipline also provides bindings, so it works properly with Scala test and specs too. So depending which test library you like. And what it's all about is defining your properties into rule sets and then calculating out what's the appropriate rule set to check. So we have laws coming from monoid, which is a semigroup, so we have laws coming from semigroup. And so those are going to be some of the same laws. So we don't want to check them more than once. So discipline is going to do that calculation to say, I only need to check this one once. It came from two different places. That one's a different one, so I do need to include it in the list of rules to check, so on. Cats defines all of its laws in a separate suite. This is in the cats/test hierarchy and published as cats-test, cats-test in Maven and so on. There is a trait for each of kind of its type classes that specify the laws for those type classes. So this one is for monoid K, which is a monoid with arbitrary arity, I think. Which again is built on semigroup K, as you'd kind of expect. Specifies the left identity and the right identity. It's going to yield an is equal, telling us whether or not those two sides, the left-hand side and the right-hand side, are equal. That syntax, less dash greater, is our equivalence for these two different ways. So combining the empty and A should be the same as A. Combining A and the empty should be the same as A. So then the machinery is in Cat's Law's Discipline. There is a trait called type tests for each of the type classes that it has. So there's a monad test and a monoid K tests and all those kinds of things. Monad extends applicative, so same kind of thing. These things end up mirroring the ones that we just looked at in the laws traits. So there will be a monoid K laws that extend semigroup K laws, and a monoid K tests extend semigroup K tests. And in this case, monad actually is based on both applicative and flat map, so they're both there. It's going to define this monad, this def monad that generates our rule set. In this case, we're parameterized in 3 things. The number of parameters vary depending on the type class. So monoid doesn't have as many. Monad has 3 because it's a monoid of some instance, and then you flat map to get to some other type, and then if you're composing, you'd have an A and an A to B, a B to C, and you want to be able to go A to C. So you might be the same types, or you might want different types. This takes a ton of implicits. There's probably 8 or 10 implicits that come into there because you have equals instances and arbitrary instances for a bunch of different combinations of things. And that yields a rule set. You probably don't need to touch this unless you write your own set of laws. So now let's look at my implementation. So I have my option of A. It has 2 versions, a my none and a my sum, where none has nothing. It's just an object, single instance. My sum is parameterized in the A and just has that A as a value. And now I'm going to make a monad instance for my option. So cat's monad calls the apply the unit. They call that pure. So I have to implement a pure, which is going to take my A and wrap it into my monad context. Flat map is parameterized in A and B, and it's going to map a function A to monad of B. I'm going to have to implement that. Cats also has this weird tail rec m thing, which is about trampolining into a tail recursive version of your flat map. It's really kind of confusing. Actually, I haven't reread documentation. Maybe the documentation's improved, but this is what got me into checking laws in the first place. How do I know that I implemented this tail rec m correctly? Let's run the laws and see. I have my equals and my arbitrary. So equals for my option. I haven't shown you the implementations for any of these. Eventually, I'll have example posted that has all these implementations. But basically, if they're both my none, it's the same. If they're both my sum with the same value, then it's the same. My arbitrary is a little more interesting. I am going to return one of either a constant my none or an arbitrary value mapped into a sum. One of, I believe, is fairly equal percentage of each of the values. So 50-50 chance that it's a none or a sum with some value. Now that I have this, I can write my tests. So my option spec, again, I'm a fun suite and a matchers, and I've mixed in discipline. And once I've done that, then I can call check all. My option of int is just label stuff. And the interesting thing that I'm going to check is monad tests parameterized by my type dot monad with the 3 parameters that I want to do. So here I've just done it int. I could do some other types as well. Check multiple ones here. So monad tests, remember, is coming from this discipline machinery, and this monad method is going to generate that rule set. So this is saying check all the rules in that rule set with these parameters. And I run that, and I get something that looks fairly happy. At least it's green. So we're going to see here it's going to have run tests on all the applicative laws, all the covariant laws, flat map, invariant, monoidal, blah, 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 blah. If I write a law badly, or write an implementation badly so it fails the law, Now it'll tell me that an exception was thrown during the evaluation. I falsified it after so many evaluations. I expected this value and I got back a my none instead. Incidentally, to make that fail, I just made all this stuff return my nuns. So takeaways. So laws separate good behavior of your classes from the domain behavior of whatever your thing does. Make sure that your monad instance, whatever monadic context you're trying to chain through, that's the domain logic that you're testing in your domain tests. But the behavior and making sure that it's consistent is coming from the laws. By testing the lawfulness, we ensure that our implementations are going to behave correctly when we pass our instances to various algorithms. Property testing is a really good mechanism for us to test the lawfulness. Generate a bunch of example randomly generated inputs, check that the properties still hold. And Cats and Scala Z both have suites of laws. So when we're writing our instances of type classes against either of those libraries, we can use the testing mechanism of those libraries to make sure that the laws hold for our instance. And then that gives us the confidence that we can call other methods within those ecosystems and know that our instances are going to work within those. So this is my Twitter, and this is where examples to this will be. I'll be posting these slides, and I'll tweet out when those are there. And then I'll have examples for all of these probably up by the end of the week. Any questions? Yes.
I have a question about property testing.
Yes.
Sort of slightly tangential. What always concerned me, and maybe it's, you can show me that there's a method to solve the problem. What I was always concerned about with this is, I didn't like the randomness of it with respect to edge cases. I would always want edge cases tested, always. I wouldn't want it to be a random thing that might show up. Is there a way to set up the property test such that edge cases always get fulfilled and then?
So the question is there a way to force edge cases to be tested? So one answer is you don't have to use property testing by itself. So absolutely you should probably have some tests or specific tests around specific inputs that you know are going to be problematic. Secondly, depending on the structure that you have, you could probably set up your arbitrary instance to bias correctly. So all of the kind of basic in-eval sort of arbitraries are already going to be biased towards things that we know in general are typical edge cases for those types. So like I said, ints, zeros, minus ones, max ints, and so on. But if we knew, for example, that we were more likely to have edge case in my option around nuns, I could set it up so that I'm more likely to generate nuns than anything else, right? So that same gen.oneof that gave me the two different, I'll pop forward to that. Actually, there's one right on here. So this gen.oneof, it's going to give me these 6 values with roughly equal percentage. I think there's another variant of this that I can specify the distribution, so I'm more likely to get another one than another one. So
there's also table-based property checks.
Yeah.
That might be helpful in that case too.
Yeah, the comment was you can also set up a property test with specific inputs and outputs that you expect using a table structure.
Are the suites of laws for Scala Z and Cats very similar, I hope?
The question is, are the suites of laws very similar? So most or all of the type classes that we have in Scala Z and Cats all come from kind of math and category theory. So a lot of these have the same thing, right? There's not disagreement between the two about what left identity should be for a monad. So yeah, they have a lot of the same laws. When we get to some of the things like that tail rec M, that's something that might be a difference. Scala Z doesn't have a similar thing to tailrec-m, so it doesn't need to have a law to make sure that tailrec-m works. But cats has this tailrec-m thing, so it has a law around tailrec-m to make sure it works. But all the kind of basic identities and associativities and all those kinds of things are going to be the same in both, specified obviously in their own syntax, but the same laws. Any other questions? Great, thanks guys.